I'm looking forward to talk about our 3D vector flow imaging work. Currently, I'm a postdoc at the Center for Fast Ultrasound Imaging, which is headed by Jørgen Jensen. So the way I will go about this talk is that first I will talk about the current clinical practice in flow estimation, talk about 2D vector flow imaging and its applications. Then I will go to the 3D velocity estimation and its potential. And finally, I will give some future perspectives seen from my point of view. So first, the rhetorical question, so why even look at velocity estimation using ultrasound? Velocity estimation is important because it gives us a good field of the cardiovascular system and what's happening in the arteries in terms of flow or perfusion in kidney or tumor. These images here is a traditional color flow imaging approach, and what we see is actually flow either towards or away from the transducer, which is here up at the top. If we want more quantitative data, the way doctors do today is that they use a spectral estimator. So you have a range gate here, and then they use these wings to adjust for the angle, to angle compensate. And the reason they have to do that is because conventionally we can only estimate ultrasound in the direction of our wave propagation. So if we send ultrasound in this direction, we can only estimate any velocity component that is parallel to this beam. By then angle correcting here, we can get the correct velocity from our spectrum. This might be easy in some cases, and here we can predict the flow direction going to the brain, but I will now show you an example where it's more complicated. Here we are in the carotid bifurcation, and here if we have traditional color flow imaging, it's actually difficult to see what's going on. We have blue colors here, red colors here, pointing towards or away from the transducer. We know in this case the flow is going from left to right, but from the image itself we can't really see it. So what I will do now is that I will superimpose a vector flow image from exactly the same place from the same time. And then it looks like this. So now we have arrows that indicate the direction of our flow, and the size and the background color indicates the magnitude of that. So if I go back again, and if you look here in the carotid bulb, you'll see now it's difficult to see what's going on. Now you can actually see there's a vortex forming. And this happens just after peak systole, and this vortex travels rapidly downstream. What we then have been working on is to add the third component, so in this case the outer plane component. So now we'll talk about the 2D vector flow technique that we have worked with a lot, called the transverse oscillation method. It was developed before my time, or before I joined the lab. But that is one that we then carried on and expanded to 3D. So as I pointed out, traditionally we can only estimate actual velocities because we only have a propagation in the actual direction. And it's this propagation that enables us to do velocity estimation. So what we do is we emit sound in the same direction several times, and then we look at the shift from time to time. It can be a phase shift or time shift, for instance. So the idea with this technique is that, well, what if we have two sources? So if we now are in the bathtub or somewhere at home and we put two fingers in the bathtub, we will create ripples. These ripples will travel and then they will intersect here in the center. And now we actually have oscillations both in the actual direction, but also oscillations in the transverse direction. And hence the name, the transverse oscillation approach. This approach has been implemented on a commercial scanner, BK scanner, and this technique has been FDA approved and can therefore be used for clinical use. So now I will show you some clinical examples of this technique in real time. So this is again from the carotid bifurcation, and here the arrows and the colors point from right to left, and here it's like blue or purple. We can see up here on the color wheel what direction that corresponds to. And now we're going up towards the carotid bulb here, and we can see the colors change. They go into purple, red, yellow, green. So we can see that we actually have this vortex forming at some points in the cardiac cycle up here. So now that medical doctors can actually see the flow and the flow direction and what's going on, and this is new information for them. I will show you another approach here. This is a scan of a AV fistula. This is typically used when people are undergoing dialysis. So you need to take a vein and put it onto the artery. The vein will arterialize, and then you can use that to insert a needle so you can clean the blood. And the flow here, and so I have a medical doctor or a colleague who's a medical doctor and a PhD student. He's trying to look here in the arterialized vein and see if he can use this 2D vector flow information to give like quantitative data of the volume flow. He of course has to make assumption of circular symmetry because he doesn't have the outer plane. He doesn't have the outer plane, right? So that's where 3D will come into the picture. I have another example here. This is a scan of the right atrium. It's performed during open heart surgery. And you can see here how the blood swirls around in the right atrium. And if you're more interested, you can find details in this paper that's coming out soon. Another example is looking at the blood coming out of the aortic valve. You can see the aortic valve is down here, you can vaguely see it, and the flow coming out here during peak systole. And this is done, again, during open heart surgery. It was a bypass surgery, so it has nothing to do with the valves. But this could actually be used during valve replacement surgery. So currently, it's difficult for the medical doctors to evaluate if they have placed the valves correctly and if the flow is back to normal, because they can't do it while they're doing their operation. With this technique, they could actually look at the flow before they replace the valves and after they've replaced the valves and evaluate it on site while they're doing the operation. So moving on a little bit further, up and then downstream, this is the ascending abdominal aorta. And this is again from the same scanner, so it's a real-time image of the secondary flow. So this is a cross-sectional image of the ascending abdominal aorta. And we can see this helix flow. So the flow in the ascending aorta has like this helix shape. What we want to do is estimate both this component and the main component, which is the outer plane component, so in direction of the flow. And eventually we want to do this in real time, of course. So that brings me to the next part of my talk, so our current research in 3D vector flow imaging. So we thought about how can we do this. So the first step we took was to think using a 2D array. And with a 2D array, we can use conventional imaging, conventional beamforming, and get this field that oscillates only in one direction, and thereby we can get the actual velocity component that we would do normally. So what we do then to get the two next components, x and y, is that we modulate our aperture here, so only the black regions here are active. And if we do this, we actually get a field that oscillates in x, but not in y. And then we can also do this the other way, so rotate it 9 degrees, we get an oscillation in y, but not in x. And so the neat thing here is that we actually don't do it on the transmit side, but we do it on the receive. So we transmit a conventional weakly focused pulse, and then we can do all this beamforming in receive. So we can get all three spatial components from the same data at the same time. So as I mentioned, we need a 2D transducer, and we have a 32 by 32 element transducer manufactured by Vermont in France. And so we have in total 1,024 elements. And we really wanted to sample from all of them. And that's why we connected it to our experimental ultrasound scanner, SARUS. SARUS is an acronym for Synthetic Aperture Real-Time Ultrasound System. And it's a really big thing, but what is unique about it is that it has 1,024 channels. And we can sample from all those 1,024 channels at the same time, and we can do it at 70 megahertz with 12-bit precision. So that gives us a unique access to the RF data of our 32 by 32 element transducer. We can then store the data in RAM and then download it to our cluster and process it afterwards. This machine also has real-time processing capabilities. So now I will show you the kind of the setup we try to get to do the flow imaging. So we have our 2D probe over here on the right, and then we have a vessel. And we have had different kind of vessel, artificial vessel, mimicking or tissue mimicking vessels, and then real in vivo vessels. So if we have a vessel here and we have it perfectly aligned, so we have a cross-sectional plane and a longitudinal plane, what will actually be coming out of the yellow plane, which is the cross-sectional plane, is this 2D circular symmetric profile. Because if you have a really long tube and we have a viscous fluid, it will become, and it's laminar, it will be fully developed, so we'll get this 2D parabolic shape. And we can use that by measuring the volumetric flow and then calculate back to the theoretical profile. So if we had used, so the question is, can we measure this outer plane velocity component with current techniques? And of course, no, with 1D techniques we can't do it. We can't do it with 2D techniques, but 3D techniques are able to do this. So if we look now at the flow in the cross-sectional plane, and this is the set component, so this is the component up and down in this image. So this you could obtain with conventional 1D estimators, and it's fairly black in the whole region. That's because there's no flow in that direction. So what I will show you now is the outer plane velocity component. Imagine the flow is actually going out here in the auditorium towards you. And then it can look like this. So we use surface plots to illustrate the outer plane velocity component. What you see up here on the left is a 3D rotation to give you a feel of what it's looking like. And then over here we have 10 frames that we recorded and that we are looping over. And on either side here you see projections of the flow profiles, and they should ideally be parabolic, and we can see that they are that to a good extent. And down here at the bottom we have isovelocity contours. They should be round if it was ideal, and they are close to being round. And we can see the velocities are highest here at the center, around 1 meter per second, as we expected from our volumetric flow rates. And we have the lower velocities here at the vessel boundary. So this was from an artificial rubber vessel in a water tank. And we also thought about how can we try to visualize it in a different way, not using only the outer plane component, but also the whole 3D information. And again, here to give you a 3D feel, and what we have are arrows that represent the vectors. So they have all three spacing components and point, of course, mainly out of the plane because that's that's the cross-sectional plane we were imaging. And again, we can see the higher velocities in the center in yellow and the lower velocities at the vessel boundaries. Then we went on and tried to measure in a carotid mimicking phantom. And we have a Shelly flow pump system here, so we can control the flow profile. And we have our 2D array, SARS, and then we can measure. So now we try to measure in two crossing planes. And so now it becomes a little bit complicated to visualize it. As we just heard before, getting the data is easy. Trying to visualize it is the tricky part. So what I will do now is I will show you the individual components one by one. So we have our two planes here, orthogonal to each other, and we have the actual velocity component here in the center. And again, it's more or less black because there's no flow in this direction because our transducer flow direction is parallel to our transducer surface. If you then look at the y component, so that is the component that goes out in this direction. And there's a little bit of component in this direction, and it's mainly because we have a little bit of a tilt on our angle on our two planes, so they're not 100% transverse and longitudinal. And if you now look at the main flow direction, which is in the x direction, then this is what we get. We have velocities getting close to around 70 centimeters per second. We have the highest velocity here in the center and low velocities at the vessel boundaries. So we were aiming for hitting it directly cross-sectional and directly longitudinal, but the point here is it's actually not really, it doesn't really matter because we have all three components, so we can get the correct velocity magnitude by just combining them up. So now we can get the actual velocity magnitude, or the speed if you like, here in the center, and that could be used for measuring the maximum velocity during peaks in the carotid artery, for identifying stenosis. Often medical doctors use the maximum velocity as some kind of indicator for the degree of stenosis. But as I showed before, if you have to angle compensate you don't really know what you're doing. With this 3D technique, for instance, you can get the correct velocity magnitude, regardless of transducer orientation. And I think that's really neat. So it will be much easier to scan, and then a more inexperienced operator could scan the neck and see what the maximum velocity is, could just come out of the system. So when we have the outer plane velocity component, we can also do volumetric flow imaging. So essentially all we need is just to integrate the outer plane velocity component, and so in our case just summing up all the pixels. And then this is what we get. In blue we have our flow pump, so that was set to 16.7 milliliters per second. And what we have up, the red circles here are our estimates based on our 20 frames, in mean 17.1 milliliters per second. And that gives us a relative bias of 2% and a relative standard deviation of 8%. So we can see we can also get quantitative data. We can get the volumetric flow rate that corresponds to the real values with 3D techniques. So now we'll go to our in vivo measurements. And this is an example of our clinical setup. We have a medical doctor that's an experienced geologist performing the scans. We have a healthy volunteer. And we have the Cyrus scanner up here. And we also just made a scan with the clinical scanner just to see where we are. And this is more for show. So these are the two imaging planes we had, the ZX and the ZY plane. And in this case, we only estimated velocities along the center line, MO, because that was the first experiment we did. And what I will show you is only velocity here at the center of the vessel. And what we get, so note that main component is here in the X direction, but this beam mode image indicates that we're a little bit, again, tilted or at an angle. So this is what we get, our in vivo M mode in 3D. On top we have in black the actual velocity component, or I should say the reset component. It's very small relative to the others. In yellow we have the Y component, and the main flow direction is in X, so Vx has the largest component here. And we can see this pulsatile nature that we would expect. If we then look at the velocity magnitude, we see the peak systole here, then we have a small peak, and then it goes down to the end diastole and then repeats that. And that's a very common pulse shape in the carotid artery. And so we did a scan with a conventional scanner trying to hit the same location. We didn't, of course, we couldn't do it at the same time. So this is more for like a qualitative comparison. So we took the spectrogram and just underlined it here just to illustrate that the shape we actually get is very similar to what we would get with the clinical scanner. Of course, the clinical scanner we had to angle compensate, so we don't know if it's true or not. With 3D vector flow, we get the correct velocity magnitude. And what I will show you now is a video of these vectors here at the center of the vessel. The black is so small you can't see it. And then you have the X component in purple and the Y component in yellow. And then the resulting vector is the red one. You can see how it points out here. Again, we have a small angle on our orientation. And down here you can see the absolute trace. And I've slowed this down from 75 Hertz to 15 Hertz so you can actually appreciate what's going on. So here, large arrows pointing out during peak systole coming now, and small arrows during the diastolic phase. So that brings me to the next step, and we want to do, of course, more research, and more specifically in real-time imaging and scanning more volunteers, and not in M mode, but also in our two planes, and eventually, of course, in longer perspective, also in 3D volumes. And this brings me to the last part of my talk, is where I see the future of ultrasound is going. So I see that ultrasound is going to be smaller and smaller. At least the technology is capable of doing it. It can be from advanced smaller scanners to really small portable ones you can just bring anywhere you want. But it's at the same time it gets more and more powerful, either because we can use TPUs in the scanners, or we can use cloud computing, have clusters that just processes all the data. And so the field is really expanding, and I'm sure that Tom Saber will talk more about that after lunch. And so it's really interesting to see how ultrasound is spreading and getting more and more applications. And then I just want to pull out one example here. Is from Philips, the new EPIC scanners, EPIC 7 up here. It's a new technology. I put that in quotations because it's been there for a while, but now it's in the scanners. And these figures are from their presentation of the new scanner technique. They call it Insight. Essentially, the way I see it, it's synthetic aperture. This is the conventional focused beam where you have the good focal point in the focus, but then you get blurred images. But with synthetic aperture, if you use transmit aperture appreciation, you can actually get a good focus in all depth. So that's actually synthetic aperture is now coming to commercial scanners, and that also gives a number of other advantages. One can do high frame rate imaging, because either using synthetic aperture or plane waves, we can get a much higher frame rate, both for beam mode, but of course also for flow. And this is an example from a colleague of mine from years ago, where he used plane waves to get 100 frames per second. And again, carotid bifurcation, and you can see the vortex forming right here, but then rapidly traveling downstream. And here again, you can see the vortex forming. Another thing one can do is one can look at slow flow and perfusion. And for that, because there was a lot of talk about brains yesterday, I took a couple of slides from Michael Tander's group. And it's from a rat brain, and they have the scanner here on top, and then they inject 4-AP to induce epileptic seizures. And what you will see in the next video is the change in the blood volume in the brain. And these are actual velocity components only, but you can still appreciate that you can actually image really slow, small changes here in the rat brain. So that is a plane wave approach where you can get really high frame rates and you can image slow changes, and we can do that with these techniques. And I also think that both 2D and 3D vector flow will become really important. People are still investigating what extra information it's giving. It can be used for functional imaging. This is an MRI image of the heart. We have the pulmonary artery and the aorta. And ultrasound is not here yet, but I envision that ultrasound can get here with time, where we can capture this flow, and we can also get the temporal changes. We can then visualize the pathology, looking at deficient heart valves and so on. And then I just want to say, well, we can also get maybe even new parameters to look at. Say, for instance, pressure gradients. I have a colleague who's looking at pressure gradings, and what he's using is the vector flow data. He puts that through Navier-Stokes equation, and then with some assumptions, he can get the pressure gradients. And we can see how here it pulsates during the cardiac cycle. So that brings me to this, that we get quantitative data. And I think Michael also will also talk about quantitative data. I think this is where ultrasound can have a really strong point. We can get the full velocity vector, we can get volumetric flow rates, and we can get new parameters like the pressure gradients, or maybe even pressure in a longer time. And this is the thing where ultrasound has a really strong point, that we can more or less in real time get quantitative data. So we're removing some of the subjectivity that operators introduce currently in diagnostic criteria. So that just brings me to the summary. With 3D vector flow imaging, we can get the correct velocity magnitude, so we're not limited by the conventional angle dependency. We can get real-time 2D vector flow imaging, and I've shown you some of the clinical applications, and people are currently investigating and seeing, is there any new information useful for the medical doctors? And I'm sure there is. And finally, I've presented some in vivo, one example of in vivo 3D vector flow imaging, and we can also, in the longer run, get neuroparameters like pressure gradients. So now I just want to thank my group at the Center for Fast Ultrasound Imaging and our funders down here. Thank you for your attention.
lunch. I think we have an extended lunch, but thank you very much.
Thank you.